This just to show it more simplistically, before 95, it is limited to spawn along the European continental shelf, which also can be showed by fishery and also other data. So they are limited to here when it's cold. Now we know that in the 60s it was much warmer, and from this larva data, we also know that spawning activity happened on, for example, Rockall and further north. So it is a valid question to ask, okay, so has this dynamics also taken place after 95, since that was like the 60s? We have no larva data, unfortunately, now, but indeed, fishery indicates that there has been a large shift out towards the bank. So just to conclude this part is that the spawning distribution has shifted both north and west after 95. And possibly this has led to better recruitment of young fish and thereby much larger stock, larger fishery. Just the exact reason is if this is more food, larger spawning area, faster larva growth due to higher temperatures is open. So this is an area for research now. Okay, how will this influence the migration past the Faroes after spawning? But to understand that, we need to have a basic understanding of the main currents. This is the outline of the subpolar gyre itself, one branch of the North Atlantic current. Then we have the continental shelf current, warmer, close to the continental shelf. And between there we have a more variable flow along Rockall, which partly splits towards the Faroes and partly towards Iceland. And we also need to know that after spawning, these fish are exhausted, so they will not oppose the main flows, they will just drift with them, largely. That means that during cold years, when they are limited to spawn here, then these exhausted fish will just follow the main flows and thereby drift in through the Faroe-Shetland Channel. On the other hand, when it's warmer, the exhausted fish are situated in a completely different flow regime, and they will drift more to the west of the Faroes, the Faroe Bank Channel, and towards Iceland. And without going into detail about this, we have some data to show that this actually has happened. And the implication, for example, of this is that when they migrate through the Faroe Bank Channel, they're much more congregated, they're much denser shoals, they're more fishable. So this has economic implication for the fishery. Just in conclusion, which you can read yourself, and take a sip of glass water. So clearly they choose different paths depending on ocean climate, and that has implications for fishery and economy. Then I'm just gonna speculate, this is a different ending of the story. Of course, understanding how marine climate is influencing this big stock is important for good harvesting of or management of this fish stock and good assessments in the future. But I've changed the end here to be more in line with this, the ideas of this conference. It is how scientists and the fishery can maybe collaborate better together and maybe thereby also reduce CO2 emissions and reduce costs. So this is not purely science fiction, but some visions. When warm water meets colder water, you have fronts between there. And along fronts, things congregate, not just rub plastic or so, but also, for example, plankton, and thereby also fish. So fish are associated with subsurface oceanic fronts. These fronts are not static as here, they move around, and information on where a front is at any given time is of value to the fishery. And this, for example, shows this image from satellites based on the sea surface temperature. It has been handled in order to enhance the oceanic fronts, and you see it's highly variable, both in space and time. So it could be, for example, the region I showed you before, you have warm water meeting cold water. So somewhere between there, you should expect fish to congregate. And that would be a good region to fish, for example. But there's no way that a skipper on a blue whiting trawler here would know that the front is just there today. So it has to steam around to relocate this fish until it can find the fish and begin fishing. And of course, having these big ships steaming around burns a lot of oil and thereby has a huge CO2 outlet. And there, I think we from oceanography maybe could be working with the fishery industry to help this problem. I talk about this to draw your attention to a talk that will be in the workshop 4 by Peter Rines about these so-called sea gliders. They're small, if you want, submarines. They are torpedo-like with wings, and they swim in the ocean by themselves. For example, here you get from satellite, you can tell this sea glider where it should go. It dives down to the bottom or 1,000 meters and up again. And along its path, when it flies down there, it measures things like temperature, salinity, oxygen, fluorescence, currents. So lots of data down there. When it comes up there, in almost real time, it sends data right back to the institute, gets new position, and it continues. And this is a project that is ongoing between Fiskerannsóknarstofan now and the University of Washington. So I'd say this is maybe one of the very few true transatlantic initiatives that are already ongoing, also in line with this conference. So could we have weather forecast in the ocean, like we have in the atmosphere? We could have sea gliders swimming here, and this sea glider would know that the front right now is there. And if you could be collaborating with a big blue whiting or some other pelagic fleet, they could maybe help with the logistics to deploy and recover these things, maybe help funding them. So we could have many more in the ocean. These things are all sending data right back to the satellites. So this, in combination with models, of course, and the satellite data, you could actually come up with a map like this for every day. Say, how are the fronts today? And this information would be very valuable if you could get that message back to the ships. So instead of just steaming around, you could say, the front is there, so go there. Don't go other places and spend energy, which would reduce cost and CO2 emissions. I think this is not purely science fiction. It is doable. But it requires a lot of collaboration, of course. So without more complication, I'll just say that there are very large changes in the marine environment in the Northeast Atlantic, which influences blue whiting and also other components of the ecosystem. This knowledge is, of course, if it can be put into the stock assessments, which Fiskerannsóknarstofan and ICES use, they could be more accurate, for sure. And also that here is a potential for collaboration between this big fishery and the scientists, which could reduce CO2 emissions and costs and other. So just to maybe initiate some discussion. Thank you.